Hello. Whether voice is audible? Yes or no? Give the reply. Okay. Whether screen is visible to everyone? Give the reply. Whether screen is visible? Okay. So we'll start our lecture. So in the last lecture, we have seen that primary refrigerant and different types of primary refrigerant. So now, so in the last lecture, different types of primary refrigerant means we have seen what is meant by halocarbon refrigerant, what are the different types of, what are the different refrigerants which are coming under the halocarbon types of refrigerant, how to give the nomenclature system for halocarbon refrigerant, and we have seen the some of the specific properties related to that halocarbon refrigerant. In the same way, we have seen for azeotropy refrigerant, then for inorganic refrigerant, and lastly, we have seen for hydrocarbon refrigerant. Now, second main category of refrigerant or second main classification of refrigerant is nothing but the secondary refrigerant. So, what is meant by secondary refrigerant? The refrigerant which are firstly cooled by the primary refrigerant. The refrigerant which are firstly cooled by primary refrigerant, and then it is used for cooling purpose. Then such type of refrigerant will be called as a secondary refrigerant. So, under secondary refrigerant, that secondary refrigerant is also called as a brine solution, or it is also called as a antifreeze also. So whatever secondary refrigerants are there, those are of two types. First one will be called as a water, and second one will be called as a brine solution. So out of that water, when to use water as a secondary refrigerant? So when we require to maintain a temperature, when we require to maintain a temperature above 0 degree centigrade, when we require to maintain a temperature above 0 degree centigrade, for example, consider example of central air conditioning plant. Suppose you are obtaining that, or you are opting that central air conditioning plant for any of the mall. So whenever you are opting that central air conditioning plant for any of the mall, then the desirable or required temperature which you want to maintain inside the mall will be in between 18 to 25 degrees centigrade. So for achieving that, whatever supply air or whatever air we are going to supply to that central air conditioning plant, that temperature of that air should be in between 15 to 18 degrees centigrade or 12 to 18 degrees centigrade. So to obtain the 12 degree centigrade air, to obtain the or to cool the air up to 12 degrees centigrade, you can cool the air up to 12 degrees centigrade by using the chilled water, which will have the temperature in between 5 degrees to 10 degrees centigrade. So with the help of chilled water, you can obtain the air which will have the temperature in between 12 to 18 degrees centigrade, and with the help of that air, you are able to obtain or you are able to maintain the temperature inside the mall between 18 to 24 degrees centigrade. So here, to chill the water, to chill the water up to 5 to 10 degrees centigrade, we are using the primary refrigerant. And with the help of primary refrigerant, you are cooling the water up to 5 to 10 degrees centigrade. And after that, whatever 5 to 10 degrees centigrade chilled water you are having, that chilled water you are using for absorbing the heat from the air. That means here, whatever secondary refrigerant, that is nothing but water, that is first cooled by the primary refrigerant, that is first cooled by the primary refrigerant, and then it is used for heat absorption process. So that will be called as a secondary refrigerant. So here water will be acting as a secondary refrigerant. Water will be acting as a secondary refrigerant. But when we want to maintain temperature above 0 degree centigrade, when we want to maintain temperature above 0 degree centigrade, second type of second refrigerant is nothing but the brine solution. So here brine is nothing but it is a mixture of water. It is a mixture of water plus salt. Plus salt. So what is the limitations of using water as a secondary refrigerant? Suppose I want to maintain a temperature below 0 degree centigrade. So with the help of water as a secondary refrigerant, whether it is possible? So it will not be possible because freezing point temperature of water is nothing but 0 degree centigrade or 0 to 4 degree centigrade. So with the help of that water, we are unable to obtain a temperature below 0 degree centigrade. We are unable to obtain a temperature below 0 degree centigrade. So in that case, we cannot use water as a secondary refrigerant. So instead of water, we have to use brine solution as a secondary refrigerant. Now, what is meant by brine? So brine is nothing but it is a mixture of water plus salt. So that salt may be NaCl, or that salt may be CaCl2. CaCl2. That means sodium chloride, that is nothing but meat, or that is nothing but salt, and CaCl2 is nothing but calcium chloride. So whenever you are mixing NaCl, that is nothing but sodium chloride, inside the water, the freezing point temperature of water, will decrease from 0 degree centigrade to minus 21 degree centigrade. So whenever you are mixing salt inside the water, the freezing point temperature of that brine solution will decrease up to minus 21 degrees centigrade. And instead of NaCl, if you are going to mix CaCl2 means calcium chloride. So whenever you are mixing calcium chloride inside the water, initially the freezing point temperature of water was 0 degree centigrade, but because of mixing the CaCl2 inside the water, the freezing point temperature of that CaCl2 brine solution or calcium chloride brine solution will decrease up to minus 56 degree centigrade, near about minus 56 degree centigrade. So because of using brine solution, you are able to maintain the required temperature below 0 degree centigrade, because that brine solution will have the freezing point temperature below or well below than 0 degree centigrade. That is for NaCl brine solution minus 21 degree centigrade, CaCl2 brine solution, that is minus 56 degree centigrade. Sometimes instead of salt you can use the glycol also. Inside the water. That glycol may be ethylene glycol, or that glycol may be propylene glycol. That glycol may be ethylene, or that glycol may be propylene glycol. So whenever you are mixing glycol along with water, then also whatever brine solution will be formed, that brine solution will have the temperature. That brine solution will have the temperature below 0 degree centigrade, and because of that, you are able to use that brine solution for achieving the temperature or achieving the required temperature below 0 degree centigrade. So this is related to the secondary refrigerant. Now, next point we have to see, that is nothing but property of a refrigerant. How we are deciding which type of refrigerant we should select for a particular application. Suppose we are considering one application. Suppose we are having cold storage plant. And suppose for cold storage plant, I want to design a refrigeration system. And suppose I have designed the refrigeration system, but at the time of designing the refrigeration system, I need to decide which type of refrigerant or which refrigerant should I select. So depending upon which parameter I'm going to select the refrigerant, for particular application, can anyone tell me? Can anyone tell me, depending upon which parameter I'm going to select the refrigerant for any particular application? Anyone can unmute yourself and can tell me. Can anyone tell me whether my voice is clear or whether my voice is audible? Yes or no? Valsange,
Yes, sir.
unmute yourself.
Audible.
Valsange.
Yes, sir.
Depending upon which parameter I am going to select particular refrigerant for particular application.
Sir, it is depend on according to application.
But
What
for particular
purpose we can
application,
use?
how I am going to select whether it is the case that same refrigerant I am going to select for all the refrigeration system. म्हणजे
No,
समजा
no,
माझ्याकडे फक्त मला एकच रेफ्रिजरंट माहित आहे, मला समजा अमोनिया माहित आहे आणि तो अमोनिया मी प्रत्येक ठिकाणी वापरतोय, असा आहे का केस?
nahi,
Whether I am using ammonia for all the refrigeration systems? Not. Why?
not.
Why I am not using the ammonia for all the refrigeration system? This is that ammonia is also one type of refrigerant, no?
Ah, yes.
Or why I am not using R11 or R12 for all the type of refrigeration system?
According to properties made.
So selection of refrigerant is depend upon the property which that refrigerant is possessing. So according to the property which that refrigerant is possessing, we have to according to the property which that refrigerant is possessing, we have to select the proper refrigerant or particular refrigerant for particular application. Now, what are the different type properties? What are the different properties depending upon which? What are the different properties depending upon which we have to select particular refrigerant for the particular application? So, any of the refrigerant will possess three type of property. Any of the refrigerant will possess three type of property. Out of that, first type of property is called as a thermodynamic property. First type is called as a thermodynamic property. Second type is called as a chemical property. That chemical property is also called as a safe working properties. And last type of property which each and every refrigerant is possessing, that is nothing but the physical properties. Now, by considering all these three type of property, thermodynamic, chemical, and physical properties, by considering all these three type of properties, we have to select a refrigerant for a particular application or particular refrigerant for a particular application. Now, uh, out of those thermodynamic, chemical, and physical properties, we are going to see one by one each and every property in detail. So out of that, first property is nothing but thermodynamic property. Now, what is meant by thermodynamic property? Can anyone tell me which are the or what is the property which is belongs to the thermodynamic property? Can anyone tell me? Anyone? So there are different properties or for each and every refrigerant will possess different properties. So out of that, under thermodynamic category, the property which are coming under the thermodynamic property is nothing but, first one is nothing but boiling point temperature of that refrigerant. First one is nothing but boiling point temperature of that refrigerant. Second one is nothing but freezing point temperature of that refrigerant. Then third thermodynamic property is nothing but evaporator and condenser pressure. Evaporator and condenser pressure. Then next one is nothing but critical temperature and critical pressure. And last thermodynamic property is nothing but latent heat of vaporization. Latent heat of vaporization. So what do you think? What should be the boiling point temperature of that refrigerant? So boiling point temperature of refrigerant should vary or depending upon application. Wait for 1 minute. Only for 1 minute. Okay. So for particular application or for each and every application will require the different temperature range. If you are going to consider, suppose you want to design a refrigeration system for cold storage plant, and in that cold storage plant, suppose you want to store the vegetables. So there your required temperature range will be suppose 10 to or 15 to 20 degrees centigrade or 15 to 25 degrees centigrade. Suppose your second application is nothing but you want to design a refrigeration system for ice manufacturing industry. So in ice manufacturing industry, to produce the ice, whatever required temperature will be there of that refrigerant, that required temperature of that refrigerant will be below 0 degree centigrade. That means that should be minus 20 to minus 40 degree centigrade. That should be the temperature range inside the evaporator of that refrigerant. The next application is, suppose you want to design a refrigeration system where you want to you are having the uh, uh, you want to produce the liquefied oxygen or liquefied gas. That means suppose you want to manufacture oxygen, or you want to obtain a liquid nitrogen, liquid hydrogen. Likewise, there also the temperature range will be different. Their freezing point temperature range will be different. That means depending upon a particular application, we have to choose the selective, or we have to choose the we have to elect one refrigerant. Now, out of those thermodynamic properties, first property is nothing but boiling point temperature. So in general, now afterwards, whatever I'm talking related to the refrigerant, that I'm talking in general related to the in general refrigerant. So boiling point temperature. So the boiling point temperature of that refrigerant, boiling point temperature of any particular refrigerant should be as low as possible. What happens if boiling point temperature of refrigerant will be high? Suppose your application is you want to manufacture a ice, and suppose you are choosing R11 as a refrigerant for manufacturing of ice. Whether it is possible to obtain a ice with the help of R11 refrigerant? Whether it is possible? Yes or no? Whether it is possible to use the R11 refrigerant in a ice manufacturing industry? Yes or no? Can anyone tell me? Can anyone tell me? So it will not be possible to use the R11 refrigerant inside the ice manufacturing industry. Why? Because if you see the boiling point temperature of R11, boiling point temperature of R11 is nothing but 23.77 degrees centigrade. That means near about 23 to 24 degrees centigrade positive. So whether it is possible to obtain a ice with the help of that R11 refrigerant, it will not be possible. So you have to choose the refrigerant which will have the boiling point temperature as low as possible. If boiling point temperature of that refrigerant will be higher, then what will happen? Then refrigerating capacity of that plant will goes on reducing. Refrigerating capacity of that plant will goes on reducing. So the boiling point temperature of different refrigerant, boiling point temperature of that of various refrigerant is likewise. So if you are going to consider R11, that R11 is having the boiling point temperature not 23, it is 21.77 degrees centigrade. R12 is having the boiling point temperature as a minus 29. R21 is having the boiling point temperature as a 9 degrees centigrade. That means at atmospheric pressure at 9 degrees centigrade, that R21 refrigerant will get converted from liquid to vapor. R22 will have the boiling point temperature minus 41. R30 39.8 degrees centigrade. R40 is having minus 23 degrees centigrade. R113 is having plus 47.6 degrees centigrade. And R717 is having the boiling point temperature as a minus 10 degrees centigrade at atmospheric pressure. Then second thermodynamic property is nothing but freezing point temperature. So here, whenever you are going to select any refrigerant, depending upon the property called as the freezing point temperature, then you have to select the refrigerant in such a way that the freezing point temperature of that refrigerant, should be well below than the evaporating temperature. Should be well below than the evaporating temperature. Suppose if you are selecting any refrigerant which is having the freezing point temperature as a 0 degree centigrade. Suppose I am going to consider water. You have selected water as a refrigerant and which is having the freezing point temperature as a 0 degree centigrade water. And that water, suppose you are using for manufacturing of ice. So whenever you are manufacturing ice, then to manufacture the ice, that means to produce the to convert the water into ice, you require to maintain the temperature of that refrigerant inside the evaporator in between, suppose minus 10 to minus 20 degrees centigrade, minus 10 to minus 20 degrees centigrade. So whether it is possible to obtain minus 10 degrees centigrade temperature inside the evaporator with the help of water, that water should be in the form of liquid. So it will not be possible. So while selecting the refrigerant, you have to select that refrigerant in such a way that freezing point temperature of that refrigerant should be well below than the operating evaporator temperature. Operating evaporator temperature. The various values of freezing point temperature for the various refrigerant is nothing but this table is indicating the freezing point temperature values for various refrigerant. R11 is having the freezing point temperature as a minus 111 degree centigrade. R12 is having the freezing point temperature minus 157. R22 minus 160. R717 minus 77. And R764 minus 75 degrees centigrade. One mistake what I have observed here. Here, actually, the boiling point temperature of R717 should be minus 33 degrees centigrade. It is minus 33. That minus 10 degrees centigrade is for R764, that is sulfur dioxide. And for ammonia, the boiling point temperature is minus 33 degrees centigrade. And freezing point temperature of ammonia is nothing but minus 77.8 degrees centigrade. That is the correction. Now, next point or next thermodynamic property is nothing but evaporator pressure and condenser pressure. Next property is nothing but evaporator pressure and condenser pressure. So in the tier diagram, we have seen that there will be one evaporating pressure line, there will be one condenser pressure line. So for a particular application, the evaporating pressure and condenser pressure is deciding how much lowest temperature we can achieve, how much lowest or how much highest temperature we can achieve inside a evaporator. So that will be the deciding factor is nothing but evaporating and condensing pressure. So while selecting any refrigerant depending upon evaporating and condenser pressure, we have to select the refrigerant which will have the both values of evaporator and as well as condenser pressure as a positive. Why it is requirement? Wait for 1 minute. Why it is requirement? If suppose your evaporating pressure is below atmospheric pressure, that means vacuum pressure. Evaporating pressure is vacuum pressure and condenser pressure is a positive pressure, positive gauge pressure. So if you are operating evaporator at a vacuum pressure and if there will be leakage, by chance if there will be leakage inside the pipe of that evaporator, then what will happen? Instead of leaking the refrigerant, that refrigerant or that system will absorb the air. That system will suck the air from the atmosphere. And there will be the mixture of air as well as refrigerant. So that will not be the desirable case. So here, while selecting any of the refrigerant, depending upon this property, condenser and evaporating pressure, you have to select the refrigerant which will have the evaporating pressure as well as condenser pressure as a positive value. That means above atmospheric value, and it should be nearer to the atmospheric pressure, and it should be nearer to the atmospheric pressure as possible, because we are knowing that whenever you are decreasing the condenser pressure, the value of COP will goes on increasing, and whenever you are increasing the evaporating pressure, the value of COP will also goes on increasing. So to increase the value of COP of any of the VCRS system, you have to select the refrigerant which will have the both values of evaporating as well as condenser pressure as a positive, and it should be nearer to the atmospheric pressure as possible. So next point is nothing but positive pressure. Why it is necessary? Because in order to prevent the leakage of air and moisture inside the system. So as I have told you that if evaporator pressure will be negative, then because of leakage, there may be the chances that air as well as moisture will be sucked by that system in by that system, and there will be the mixture of that air as well as moisture along with refrigerant. And if opposite case will be there, that means instead of having that evaporating and condenser pressure nearer to the atmospheric pressure, so if those values will be very much high, if you are going to consider the carbon dioxide as a refrigerant, then to convert the carbon dioxide, that means from vapor carbon dioxide into liquid carbon dioxide, so vapor into liquid or conversion of vapor into liquid will takes place inside the condenser. So to convert that vapor into liquid carbon dioxide, we require to maintain a pressure near about 70 bar, near about 70 bar. So if you want to design any of the system, any of the refrigeration system which will handle the 70 bar pressure, which will handle the 70 bar pressure, then you can imagine that what should be the or how much that system will become as a robust system, or that system we require to manufacture as a stronger system. That means that will be the robust system, and initial cost of that system will be very much high. So that should not be the case. That means evaporating as well as condenser pressure should not be much more higher than the atmospheric pressure. Whether my voice is breaking? Whether my voice is breaking? Swami, can you unmute yourself? Okay, now it is clear. Okay, so this is related to the evaporator and condenser pressure. Evaporator and condenser pressure. Now, next point is nothing but critical temperature and critical pressure. Now, can anyone tell me what is meant by critical temperature and critical pressure? So, if I am going to consider in pH system or TS diagram, suppose this has a pH diagram or TS diagram. So, this is the saturated liquid line and this is the saturated vapor line. So, where that saturated liquid and saturated vapor lines are intersecting, that point will be called as a critical point. This point will be called as a critical point, and pressure corresponding to this point will be called as a critical pressure. Pressure corresponding to this point will be called as a critical pressure. Similarly, in case of TS diagram, also, suppose this has a TS diagram, this has a saturated liquid line, suppose this has a saturated liquid line and this has a saturated vapor line. So where that saturated liquid and saturated vapor lines are intersecting, that will be called as a critical point, and the temperature corresponding to that will be called as a critical temperature. So while selecting any of the refrigerant, for a particular application, depending upon the factor called as a critical temperature and critical pressure, then you have to select the refrigerant in such a way that, so before telling that, I will tell what is meant by critical temperature and critical pressure. So critical temperature, this is called as a critical temperature. So this is the critical temperature. So critical temperature is nothing but the temperature or highest temperature at which that refrigerant can be condensed to a liquid regardless of higher pressure. आता ह्या ठिकाणी जर बघितलं तुम्ही, ही जे असतो हा जो रिजन असतो त्याला काय म्हणतो आपण? सबकूल्ड रिजन म्हणत असतो. हा जो रिजन असतो त्याला काय म्हणत असतो? सुपरहिटेड रिजन म्हणत असतो. आणि बिलो क्रिटिकल टेम्परेचर काय होत असतं त्या रेफ्रिजरंटचं? सबकूलचं कन्व्हर्जन सॅच्युरेटेड लिक्विड मध्ये होत असतं. सॅच्युरेटेड लिक्विडचं परत वेट लिक्विड मध्ये होत असतं किंवा वेट पेपर मध्ये होत असतं. वेट पेपरचं परत सॅच्युरेटेड पेपर मध्ये होत असतं आणि सॅच्युरेटेडचं परत सुपरहिटेड मध्ये होत असतं. पण जर तुम्ही तुमचं प्रेशर जर क्रिटिकल टेम्परेचर पेक्षा जास्त असेल, तर त्या ठिकाणी डायरेक्टली काय होणार आहे? सुपरहिटेड वेपरचं कन्व्हर्जन किंवा वेपरचं कन्व्हर्जन डायरेक्टली कशामध्ये होणार आहे? लिक्विड मध्ये होणार आहे, रिगार्डलेस ऑफ प्रेशर. सेम इज द केस फॉर क्रिटिकल प्रेशर. जर तुमचं प्रेशर जर क्रिटिकल प्रेशर पेक्षा जास्त असेल, तुमचं प्रेशर जर क्रिटिकल प्रेशरपेक्षा जास्त असेल तर त्या केसमध्ये तुमचं टेम्परेचर, त्या रेफ्रिजरंटचं टेम्परेचर काहीही असू द्या, त्या रेफ्रिजरंटचं टेम्परेचर काहीही असू द्या, त्या ठिकाणी डायरेक्टली कन्वर्जन कशामध्ये होणार आहे, पेपरचं कन्वर्जन लिक्विड मध्ये होणार आहे, रिगार्डलेस ऑफ टेम्परेचर. सो while selecting any of the refrigerant for a particular application depending upon critical temperature and critical pressure, we have to select that refrigerant in such a way that the critical temperature and critical pressure of that refrigerant should be well above the operating condenser temperature and pressure, should be well above the operating condenser temperature and pressure. So that is the parameter called as the critical temperature and pressure. Then last point related to the thermodynamic property, that is nothing but the latent heat of vaporization. Latent heat of vaporization. Latent heat of vaporization means amount of heat required to be absorbed. Amount of heat required to be absorbed by that refrigerant to get or to convert that refrigerant from liquid to vapor. Convert that refrigerant from liquid to vapor at the same temperature. So here, suppose this is the pH diagram. This is the saturated liquid line, and this is the saturated vapor line. This is the saturated vapor line. So here, this is the saturated liquid line. This is the saturated vapor line. Saturated liquid line and saturated vapor line. So whatever this space between saturated liquid line and saturated vapor line corresponding to that pressure, that will be called as a latent heat of vaporization. That will be called as a latent heat of vaporization. System. Sorry. Hello, whether my voice is clear now? Give the reply. Okay. So whenever you want to select any of the refrigerant, depending upon latent heat of vaporization, then you have to select the refrigerant in such a way that that refrigerant should have the higher value of latent heat of vaporization. So as we are knowing that ammonia, what is the value of latent heat of vaporization at atmospheric pressure? For the ammonia, that value is near about 1395 kilojoule, 1395 kilojoule per kg. So that is the highest value of latent heat of vaporization which ammonia is possessing. So depending upon application, you have to select proper refrigerant by considering the latent heat of vaporization of that refrigerant. So this is related to latent heat of vaporization. So this table is dissipating all the thermodynamic property. This table is dissipating or indicating all the thermodynamic property of different refrigerant. So here, whatever refrigerant we have selected, those refrigerants are nothing but R12, then R22, R134A, 404A, 407A, ammonia, water, and carbon dioxide. And here we are differentiating those refrigerant depending upon various thermodynamic property. Various thermodynamic property is nothing but boiling point temperature in degree centigrade, freezing point temperature in degree centigrade, latent heat of vaporization in terms of kilojoule per kg, critical temperature in terms of degree centigrade, critical pressure in terms of bar, specific heat in terms of kilojoule per mole, and COP. So here, if you are going to see various refrigerant depending upon boiling point temperature, R12 is having boiling point temperature minus 28, R22 minus 40, R134A minus 26, R404 minus 46, 407 minus 45, ammonia minus 33. Water is having boiling point temperature 100 degrees centigrade. Carbon dioxide is having boiling point temperature minus 78 degrees centigrade. Then freezing point temperature. So R12 is having minus 157, R22 minus 160, then R134A minus 96, ammonia minus 77. Water is having freezing point temperature as a 0 degree centigrade, carbon dioxide minus 56. Depending upon latent heat, those are the various values of latent heat of vaporization for different refrigerant. If you see, ammonia is possessing highest value of latent heat of vaporization. Highest value of latent heat of vaporization. Then critical temperature. These are the various values of critical temperature for the different refrigerant. Then critical pressure of the different refrigerant. These are the various values of critical pressure for the different refrigerant. The highest value of critical pressure will be possessed by the water. Will be possessed by the water, that is nothing but 217 bar, and thereafterwards carbon dioxide 77 bar. Then specific heat. Specific heat means the amount of heat required to change. Amount of heat required to change the temperature of that substance by 1 degree centigrade, when that substance will be 1 kg. Likewise. So this is the various values of specific heat. Then values of COP for different refrigerant. These are the various values of COP for the different refrigerant. So those are related to the thermodynamic property. Now second type of property is called as a chemical property, that is also called as the safe working properties of refrigerant. Safe working properties of refrigerant. So under chemical property, the various properties are nothing but flammability, then toxicity. Third one is called as a miscibility. Next one is called as a chemical stability. And last one is called as the effect on a stored food. Effect of that refrigerant on a stored food. So one by one, here also we'll see all the chemical properties of different refrigerant. So out of that, first one is nothing but flammability, that is also called as the explosion hazard. Explosion hazard. So here, if we are going to consider ideal refrigerant, because there is not a single refrigerant that can be called as the ideal refrigerant. In the universe, there is not a single refrigerant which can be called as a ideal refrigerant. And because of the same, we are using different type of refrigerant for the different application. If there might be a ideal refrigerant, if there might be a ideal refrigerant in the universe, then we might have used the same refrigerant for all the application. But as we are not using the same refrigerant for all the application, that means there is not a single refrigerant called, that can be called as the ideal refrigerant. So if you are going to consider any refrigerant as an ideal refrigerant, then that ideal refrigerant should be non-flammable. Should be non-flammable. That means that should not form, or uh, that should not get flame, or that should not get explode whenever that will mix with the air. So ideal refrigerant should be non-flammable as well as non-explosive. If you are going to consider hydrocarbon type of refrigerant, all the hydrocarbon type of refrigerants are highly flammable. All the hydrocarbon types of refrigerant are highly flammable. That's why we are not using those hydrocarbon types of refrigerant. Then if you are going to consider ammonia, which belongs to the category of inorganic refrigerant, that ammonia is also flammable as well as explosive when that ammonia will get mixed with the air. And if you are going to consider the halocarbon refrigerant, if you are going to consider halocarbon refrigerant, then all the halocarbon refrigerants are non-flammable as well as non-explosive. Non-flammable as well as non-explosive. So if your area of application of using that PCRS system, where you require the highest priority for the safety, where you require the highest priority for safety, then you have to go for halocarbon refrigerant. Then second point or second chemical property is nothing but the toxicity. Second chemical property is nothing but the toxicity. So toxic refrigerant means which can form or which can cause the injury to human, or which can cause the suffocation to the human body, that will be called as a toxicity. So you might be knowing that carbon dioxide is toxic in nature. Carbon dioxide is toxic in nature. So here, while selecting the refrigerant, we have to select the refrigerant in such a way that that refrigerant should be non-toxic in nature. That refrigerant should be non-toxic in nature. That means it should not cause injury or suffocation to the human body whenever by leakage, or by chance suppose there is a leakage of that refrigerant, and if that refrigerant will be consumed by the human body, then there should not be injury to that human body, or there should not be the formation, or there should not be the suffocation to that human body. That means that refrigerant should be non-toxic in nature, that should be non-irritation or non-irritating to human body, that is eyes as well as ear as well as human skin also. So that is related to the toxicity. Then next property is nothing but miscibility. Next property is nothing but miscibility. What is meant by miscibility? Can anyone tell me what is meant by miscibility? So miscibility is nothing but ability of refrigerant. Miscibility is nothing but ability of refrigerant to get mixed with the oil. To get mixed with the oil, that will be called as a miscibility. So the degree of miscibility, that means how much percentage of that refrigerant is getting with or getting mixed with the oil, that will be called as a degree of miscibility. That will depend upon temperature of oil as well as pressure of the refrigerating paper, as well as pressure of the refrigerating paper. So here, while selecting the refrigerant, we have to select the refrigerant which will be miscible in nature. Which will be miscible in nature. That means that should get mixed with the oil. That should get mixed with the oil. Why? Because whenever that refrigerant will be miscible in nature, then that refrigerant will be advantageous. That will be advantageous from heat transfer point of view. that that will be advantageous from heat transfer point of view. That's why we have to select the refrigerant which will be miscible in nature. Are you getting? Then next point is nothing but chemical stability. Chemical stability means whatever refrigerants are there, whatever different types of refrigerants are there, each and every refrigerant is possessing the chemical formula or chemical bonds. So we are knowing that stability of chemical bonds is depend upon the temperature. Stability of chemical bonds is depend upon the temperature. So some of the chemical bonds are stable at the higher temperature also. So here, while selecting any of the refrigerant, while selecting any of the refrigerant, depending upon chemical stability, we have to select the refrigerant which will be chemical stable, which will be chemically stable at higher temperature also. There should not be the decomposition of that chemical formula. There should not be the decomposition of that chemical formula because of higher temperature. So if there will be the decomposition of chemical formula, that means that refrigerant will not be the, or that refrigerant will be the chemically unstable refrigerant. So if refrigerant will be chemically unstable, then whatever desired properties will be there, that desired properties will go on changing. So while selecting the refrigerant, we have to select the refrigerant which is chemically stable refrigerant. Are you getting? So that is the second last chemical property. And last chemical property is nothing but effect of that refrigerant on a stored food. Effect of that refrigerant on a stored food. Suppose you are using sulfur dioxide. Suppose you are using sulfur dioxide in a cold storage plant where you are storing flower or plants. So by chance, if there is a leakage of that sulfur dioxide, and if that sulfur dioxide will come in contact with that stored product, that means flower or plants, then there will be the, and that means because of sulfur dioxide, that flower or plant will get dry, or, or the quality of that flower or plant will get decreased. So that should not be the case. So while selecting refrigerant for any particular application, you have to select the refrigerant in such a way that by chance, if there is a leakage of that refrigerant, and if that refrigerant will come in contact with that stored product, then there should not be change, or there that should not affect on the as well as taste and quality of that stored product. So that case, or that we have to consider. So while selecting the refrigerant, we have to select the refrigerant in such a way that it should not affect on the color, taste, as well as quality of stored product when that refrigerant will come in contact with that stored product by leakage. So that is the case. That is the last property from the chemical property or safe working property. So we can summarize this. That is, while selecting the refrigerant, that refrigerant should be, or ideal refrigerant should be non-flammable. That should be non-flammable. Then that should be non-explosive. Then non-toxic, non-reacting with the lubricating oil. Then non-reacting with the moisture, and should not contaminate the food materials kept inside the refrigeration system. So we can summarize that chemical or safe working properties of different refrigerant by this summary. Then last property is nothing but the physical property. Last one is called as the physical properties of a refrigerant. So under physical property, the various physical properties of any of the refrigerants are nothing but, first one is nothing but specific volume. Second one is nothing but viscosity. Then third one is nothing but corrosive property. Next one is nothing but thermal conductivity. And last one is nothing but specific heat of liquid as well as vapor. Sorry, one more is there. I think two more are there. Order and leak tendency. So specific volume, viscosity, corrosive property, thermal conductivity, specific heat of liquid and vapor, then order and leak tendency. Those are the various physical properties which each and every refrigerant is possessing. Out of that specific volume, so how that specific volume is affecting on the refrigeration system? So specific volume of any of the refrigerant is affecting upon the compressor, because that specific, depending upon specific volume of refrigerant, we are selecting the compressor, as well as depending upon specific volume of refrigerant, the work consumed by the compressor will depend. So while selecting the refrigerant, depending upon specific volume, we have to select the refrigerant which is having low specific volume, because of low specific volume, the size of compressor will be also smaller as well as work consumed by that compressor will also goes on reducing. Work consumed by that compressor will also goes on reducing. So different types of compressor will be used depending upon the specific volume. So if your refrigerant is having low specific volume, if your refrigerant is having low specific volume and high pressure, then in that case we have to use the reciprocating compressor in case of PCRS system. If your refrigerant is having the high specific volume and low pressure, if your refrigerant is having high specific volume and low pressure, then you have to choose the centrifugal, or that is also called as a turbo type of compressor in your refrigeration system. And if your refrigerant is having the intermediate specific volume and pressure, then in that case you have to select the rotary compressor. So the type of compressor which we are selecting for designing of PCRE system, that will depend upon the specific volume as well as pressure of that refrigerant. Are you getting? So this is related to the specific volume. Then second point is related to the viscosity. So if viscosity is nothing but resistance to its own flow. So if higher viscosity will be there, then whatever refrigerant is circulating, through the PCRS system, that will not circulate with a proper speed. That means there you require to maintain the higher pressure as well as lower pressure or higher pressure range. So while selecting the refrigerant, depending upon viscosity, you have to select the refrigerant which is having the lower viscosity. Why lower viscosity? Because of lower viscosity, it will reduce the pressure drop. And pressure drop or reduction in pressure drop means you are reducing the power consumption. So viscosity, lower viscosity is always desirable. Then next one is the corrosive property. So while selecting the refrigerant, that refrigerant should not corrode the material which is in contact with that refrigerant. That means if you are designing any of the PCRS system, and for designing of PCRS system, suppose you are choosing the copper as a material for designing of that PCRS system, and through that system, suppose ammonia is passing. So if that ammonia is corrosive, because of that ammonia, if there is a corrosion of that copper, so there will not be any use of choosing the copper for ammonia system. So while selecting the any of the refrigerant, you have to select the refrigerant in such a way that should be non-corrosive in nature. So if you are going to consider halocarbon refrigerant, all the halocarbon refrigerants are non-corrosive in nature. If you are going to consider the ammonia, very much important point for aptitude. So ammonia, whenever you are choosing ammonia as a refrigerant, then whatever refrigeration system will be there, that will be made up only with the iron or steel. Apart from iron and steel, if you are going to make that CCRA system by using suppose ammonia, copper, or any of the material, then ammonia will be corrosive with any of the material apart from iron and steel. So whenever you are using ammonia as a refrigerant, then by hook or crook, you have to use iron or steel for manufacturing of that refrigeration system. Are you getting? Then next property is nothing but thermal conductivity. So thermal conductivity, obviously, the thermal conductivity of that refrigerant should be as high as possible. And because of higher thermal conductivity, the maximum heat transfer rate will take place. That means maximum heat will be absorbed. Inside the evaporator, as well as maximum heat will be rejected inside the condenser. So that is the case related to the thermal conductivity. Then next property is nothing but specific heat of liquid and vapor. So here, that is also for multiple choice question. This point is also important. So in case of liquid, you have to choose the low specific heat, or that refrigerant should have the low specific heat. And in case of vapor, in case of vapor, that refrigerant should possess the high specific heat. Why this is so? Because low specific heat of liquid will help in subcooling. And because of subcooling, we are knowing that we are able to increase the COP of system. And high specific heat of vapor refrigerant will resist to form the superheating. That means that refrigerant will not easily superheat. So if there will be the higher degree of superheating, we are knowing that there will be the decreasing COP of that refrigerant system. So we have to select the refrigerant which will resist the superheating. So that will be resisted when that refrigerant will have the high specific heat of vapor refrigerant. So always you have to keep in mind that while selecting the refrigerant, that refrigerant should have the low specific heat in case of liquid refrigerant, high specific heat in case of vapor refrigerant, because low specific heat in liquid refrigerant will help in subcooling. High specific heat in vapor refrigerant will resist in the superheating. Then next point is nothing but order. So distinct order, वेगवेगळ्या वासामुळे काय होते, that will helps in the leak detection. But that order should not spoil the taste of the food which is stored inside that refrigeration system. So distinct order is always desirable. Distinct order of refrigerant is always desirable, because of which we are able to leak detect, or we are able to detect that there is a leakage of refrigerant, but that should not spoil the taste of the food. And last one is nothing but leak tendency. So obviously that refrigerant should not have the leak tendency. So here we have completed all the properties of the refrigerant. Whatever last point is remaining, that is nothing but effect of refrigerant on the environment. That is nothing but what is meant by global warming, how that refrigerant is affecting on the global warming as well as ozone depletion, that we are going to see in the next lecture. Now you can write your roll number in the chat box and you can exit the meeting. Next lecture will be of good day, sir. Thank you. Write the roll number in the chat box.